This will be a short video about weight and how it can be different in different places. For an object on the surface of the Earth, that object could be you, the gravitational force exerted by the planet is. There's our standard gravitational force equation. Now, the crucial details: the two objects are the Earth and you. The distance that matters is the Earth's radius. And we use the mass of the Earth and the mass of you. How is that going to look on the moon? For an object on the surface of the moon, the gravitational force is going to be, here we just changed a couple of things. We replaced the mass of the Earth with the mass of the moon, and the radius of the Earth with the radius of the moon. And that would be the object's weight on the moon. Again, the crucial details. The moon and the object are the two objects. What matters is the moon's radius, and the masses that matter are the mass of the moon and the mass of the object. If we compare these weights, we know that your weight on the Earth is greater than your weight on the moon. Why is that? Well, let's look at the two equations related to each other. I've kept the greater than symbol here. We've got the g times the mass of the Earth times the mass of you over the radius of the Earth squared there, and then the same thing for the moon on the right side of the greater than symbol. You can divide out things that are common to both sides. We can take out the g and we can take out the mass of you, and all we're left with is just that mass to radius squared ratio. When one thing's divided by another, you call that a ratio. And what makes you weigh more on the Earth is the fact that the mass of the Earth divided by the radius of the Earth squared is greater than the mass of the moon divided by the radius of the moon squared. It's not just the masses that do it. It also depends on the radius. In fact, the mass of the Earth is more than 80 times as large as the mass of the moon. When we do the calculation, including the radii of both of those things, we end up finding out that your weight on the Earth is going to be about 6 times as much as your weight on the moon. Gravitational force from the Earth's surface outward. This is a graph. Not much of a graph yet. Don't have too much on here. One thing I'm going to do is introduce just sort of a transparent overlay to show you that the Earth would extend from 0 out to 1. The horizontal axis is the distance in Earth radii from the Earth's center. And so, got that blue thing to remind us that's what it's standing for. The vertical axis is the relative strength of the gravitational force, and I just arbitrarily chose that the strength of the gravitational force to be 1 at the Earth's surface. And we'll compare everything to that. Now, this particular graph only goes out to 1.2 Earth radii from the center of the Earth, so an altitude of only 0.2 Earth radii. But I wanted to put one thing on here. The solid line we have over here shows the strength of the gravitational force, and it's got a value of 1 at the Earth's surface. But something you can see is that even by the time you've gotten out here to 1.2 Earth radii, or 0.2 Earth radii above the surface, the gravitational force will have dropped down to only about 70% of its strength on the surface. So it drops off fairly quickly at first. Now, this dashed line that I drew on here represents the altitude of the International Space Station, which is 400 kilometers above the surface, or 250 miles. And at that point, the gravitational force is 88% of its strength on the Earth's surface. Well, that's interesting. That means if a person weighs 200 pounds on the surface of the Earth, they'll weigh 88% of that at the altitude of the International Space Station, 176 pounds. Let's watch a video on that, and I'll put a link to this video on the page for it.
This is air traffic control. You're cleared for takeoff.
This is a film from something called Skylab, which is a predecessor of the International Space Station. Now, here's the International Space Station early on. More has been added to it. Do those people look like they weigh 88% of what they do on the Earth's surface? These are snips from a bunch of videos that have been put together by the astronauts of amazing physics that can happen in that environment. Did it look like they weighed 88% of their weight on the surface of the Earth? It didn't. It looked like they were weightless. They're in a state called free fall. And free fall is a state you can experience anytime you want. Stand on a chair and step off. On the way to the ground, you'll be in free fall. If you're holding something in your hand when you step off, it'll feel as if that object is weightless on the way down to the ground. And that's the state the astronauts happen to be in. They're falling toward the surface of the Earth. They just happen to be going sideways fast enough so that they don't get any closer to the surface of the Earth. And we'll consider orbits here in a little while, probably in a future video. Now, if we built a huge pyramid with a flat top that's as tall as the International Space Station orbit, a 200-pound person would weigh only 176 pounds on top of the pyramid. They would not be in free fall if they're standing on top of that thing. So that would be sort of interesting. If they were supposed to take an elevator back to the Earth and they were standing on the scale in the elevator on the way down, they could watch their weight increase as they approach the ground. And I'm thinking here that the elevator is moving at constant speed, not accelerating. Or if they were at some point on the way down and the cable supporting the elevator broke, then they would be in free fall and their weight would drop to 0 on the scale. All right, let's look at the gravitational force moving a little farther outward from the Earth's surface. I've got a longer scale on the horizontal axis here. And there's my Earth drawn again. The solid line still represents the strength of the gravitational force. And again, that strength is equal to 1 at the Earth's surface. We'll look at a couple of other key points here. The dashed line here shows the altitude where the strength would drop to 1/2 of the strength on the surface. The total distance from Earth's center when that occurs would be 1.414 times the Earth's radius. I don't know if that number would ring a bell to you. It used to be something familiar to me, but I took my high school math classes pre-calculator days, so we had to deal with numbers like that occasionally. Anyway, that point would be about 2,640 kilometers above the Earth's surface, or 1,640 miles above the surface. Now, here's what the gravitational force on a person would be at that point. And I'm going to do a little bit of tricky math with that. Nothing weird. It's just going to be basic algebra and following the rules of arithmetic. So I take that expression, and when you have two numbers multiplied together in parentheses that are squared, the parentheses are squared, you square each number individually. That's what I do in the middle term here. And so I squared that 1.414, and it happens to be the square root of 2. So when you square it, you get a 2 down there, and you end up with a 1/2 here. So that's how you get the gravitational force to drop to 1/2 its value. You increase the distance to 1.414 times its initial distance. Let's go out a little farther to where the force drops to 1/4 of its value. It does that at 2.0 Earth radii from the center of the Earth. That's how far out you have to go. It drops to 1/9 of its value at 3.0 Earth radii. Okay, so at double the radius, it drops to 1/4. At triple the radius, it drops to 1/9. At 4 times the radius, it had dropped to 1/16, and so forth. Now we'll go even farther out here. The GPS satellite has an orbit radius that's about 4.17 Earth radii, and the force on it is going to be only about 1/17 of what it would be if it was sitting on the Earth's surface. And with that orbital radius, the orbital period is 1/2 of a sidereal day. Go out a little bit farther. A geostationary satellite. If you have dish network at home or one of the satellite services, you have a dish attached to your house or maybe on a post in your backyard that's aimed at one of these satellites. They're put over the Earth's equator, and they orbit with a period of 1 sidereal day. And the gravitational force on them is only about 1/44 of what it is on the Earth's surface. So gravity is definitely getting weaker with distance. Now, doesn't the Earth's gravity affect your weight on the moon? Yes, it does. So we ought to take that into account. Here's what the correct equation would be. Your weight on the moon should be written as, well, that first term there looks kind of familiar. This term here is what I gave you before for your weight on the moon. It's g times the mass of the moon times the mass of you over the radius of the moon squared. And then I've got a minus sign between these two terms. The reason I did that is because all of the Apollo moon landings happened on the face of the moon that is facing the Earth, or the side of the moon that's facing the Earth. And if you're standing there, the moon would be pulling you down to the center of the moon, but the Earth would be pulling you in the opposite direction toward the center of the Earth. If you were on the far side of the moon, we could add these two terms together, but I'll show you in a minute here why we don't have to do that. Now, for this Earth term, what I used for the distance down in the denominator, well, first of all, in the top, I've got the mass of the Earth and the mass of you. What I used in the bottom down here was the radius of the moon's orbit, because that's how far away you would be from the Earth, approximately. We might have to subtract one radius of the moon from it, but I'm just going to ignore that. It would be a small correction. So I can do a little bit of factoring with this, or a little bit of other work. Your weight on the moon would be that. I happen to write in here, replace the radius of the moon's orbit with 60 times the radius of the Earth, which is about what it happens to be. And so I have that in here. Then I can do little algebra like I did in the last term. I can square both the 60 and the radius of the Earth in that last term. And when I square the 60, I'd get a 3600 down there in the bottom of the fraction. So this last term here, well, this part of it, including the g, is actually your weight on Earth. Okay, but we're taking 1/3600th of that weight on Earth. And so that's the correction we'd have to put in to get your correct weight on the moon. And it turns out, if you make that correction, if you multiply your weight on Earth by 1/3600th, you get a number that is only 1/600th approximately as big as this thing. So to 599 parts in 600, this term here on the left is correct. And so we ignore the fact that the Earth would affect your weight on the moon a little bit. On the Earth, the moon is going to affect your weight a little bit, but it would be much less than 1/600th. And so we just ignore that. At what points on this diagram will the gravitational force be less than 1/4 of what it would be on the Earth's surface? And I give you choices A, B, or C. A is about 20 miles above the surface. That's above about 99% of the Earth's atmosphere. That guy that jumped out of the balloon 20 miles up, Felix Baumgartner, and I can't remember the name of the guy from Google that did it, but anyway, they were up a bit higher than that. Point B is about 250 miles above the surface, and that's about where the International Space Station orbits. And then point C is about 350 miles above the surface. That's about where the Hubble Space Telescope orbits. So here are your choices. A, the gravitational force at point A is less than 1/4 what it is on the surface. B, the gravitational force at point B is less than 1/4 what it is, blah, blah, blah. C, the gravitational force at point C is less than 1/4 what it is on the Earth's surface. And D, the gravitational force at A, B, and C is less than 1/4 of what it is on the Earth's surface. And E, at none of these points is the gravitational force less than 1/4 of what it would be on the Earth's surface. So you should be able to answer this correctly by now. You may have to drop back a couple of slides to figure that out exactly. As a reminder for figuring it out, the force drops to 1/4 its value at 2.0 Earth radii from the center of the Earth. Okay, that should help you out there. Here's one where we rank the planets on the diagram according to your weight on each planet from heaviest to lightest. On which planet would you weigh the most, and on which would you weigh the least? Let me show you how I can do these calculations. I've just repeated that sketch onto here. I've got planet A, planet B, and planet C, and I copied down their pertinent information. Now, if I was doing full-blown calculations with these, I'd have to have units for the radius and the mass, but I can do comparisons without having to worry about those things. but I'd have an expression like this. I'd have something like this, where I'd have the universal gravitational constant, the mass of A, the mass of U, divided by the radius of that planet squared. And I'd have something like that for planet B and planet C as well. But for comparison purposes, things that they all have, I don't need to think about. All of them would have a G and the mass of U in them, and the only pertinent information to compare them is going to be the mass of A over the radius of A squared. So that's what I'm going to compare. Mass of A, radius of A squared, to the mass of B over the radius of B squared, and the mass of C over the radius of C squared. And those are the things that I need to compare. I'd be multiplying all of them by G and by the mass of U, but that won't change their relative size. Okay, so I'd have 3 divided by 5 squared is 25. I'd have 1.5 divided by 16, and I'd have 0.5 divided by 4. And when I actually put these into a calculator, 0.5 divided by 4, I'd get 0.125. 1.5 divided by 16, I'd get 0.094. So you can already see your weight on C would be more than your weight on B. And 3 divided by 25 is 0.120. The planet where you would weigh the most is planet C. Because of its small radius, it would actually have a fairly dense planet. So you have to consider the radius of the planet. It's not just the mass. Planet A, 6 times the mass of planet C, but you actually weigh more on planet C because of that smaller size. So those are things that you have to take into account when you're doing these. Okay, here's one that I'll put a link to, and you can do this one for practice and rank them from most to least with the sketches that I happen to have here. I'll let you do that one on your own.